Now, we know from our previous studies that of all the electromagnetic waves, we already recognize one of them, and that's visible light. It turns out, though, that there are more sorts of electromagnetic wave than just light. This image, for example, is taken with the infrared type of electromagnetic wave, and then has been mapped to visible light. So this is not, in fact, a picture taken with visible light, but an image taken using a different kind of electromagnetic wave. Now, visible light, as it turns out, makes up only a small section of the electromagnetic spectrum. They tend to have a particular wavelength, based on their frequency, of course, and for visible light, this is between 700 nanometers and 400 nanometers. Now, how big is a nanometer? Well, if you remember your SI prefixes, you'll remember that 1 nanometer is 1/billionth of a meter. So there's our conversion. We need 10 to the power of 9 nanometers, that is 1 billion nanometers, before we can reach a single meter. So that means that waves of light have a very, very short wavelength indeed, especially compared to, for example, the sound waves that we're used to. So we can see that we have red at the long wavelength end and violet at the short wavelength end. From this picture, we can see that in between red and violet, we have all the other different colors, ranging from, orange, green, blue, that sort of thing. So all other electromagnetic waves are not visible. They will have a wavelength longer than 700 nanometers or shorter than 400 nanometers, and we cannot detect them with our eyes. And subsequently, we don't see them on this rainbow. Now, it turns out that we have a large number of different elements on the electromagnetic spectrum, or a large number of different types of wave. And we can see that summarized in this diagram over here. We have the wavelength on the top, and because the speed of an electromagnetic wave is always going to be the same, we'll be able to figure out the frequency as well. So in this diagram, we go from very large wavelengths to very small wavelengths. And this corresponds, of course, to very low frequencies and very high frequencies. Going from long wavelength to short wavelength, we have radio waves, which is anything longer than a few centimeters. We have microwaves, which tend to have a maximum wavelength of a couple of centimeters, and which get shorter wavelengths as we go further down. Once we start getting to very short wavelengths of microwaves, we start calling the electromagnetic waves infrared light. And as you can see, these will have quite a small wavelength rather, especially with respect to the microwave. Beyond that, at about 10 to the minus 7 meters, we have visible light. And this is all of the electromagnetic waves that we can see with our eyes. As you can see, they range from about 400 nanometers, that is 4 times 10 to the 7 meters, to 700 nanometers, that is 700 times 10 to the 9, or 7 times 10 to the minus 7. And so just as we had infrared before we got to red, we have a different sort of violet once we get to shorter wavelengths, and that's called ultraviolet. This is, of course, one of the types of electromagnetic radiation that gets to us from the sun, and of course it can cause sunburn. Now, once we get to very short wavelength ultraviolet rays, we end up turning into X-rays, which, as I'm sure you'll know, can be used to image bones. And this is because they have such high energy that they can pass straight through soft tissue and be detected on the other side. Once we get to very short wavelength X-rays, we can start calling them gamma rays. Now, it turns out that gamma rays are the shortest wavelength, electromagnetic waves that it's possible to get. Anything with a wavelength shorter than this sort of area, 10 to the minus 11, is automatically classified as a gamma wave, or a gamma ray. All of these wavelengths put together are called the electromagnetic spectrum. So the spectrum consists of all the different sorts of waves. We can call these waves a number of different things. We can call them electromagnetic waves, we can call them electromagnetic radiation, or we can call them by their individual parts of the spectrum, whether it's visible light, X-rays, gamma rays, infrared, radio waves, whatever. So how does the wavelength of an electromagnetic wave relate to the amount of energy it carries? Well, as I'm sure you can guess, radio waves have a fairly low amount of energy, whereas ultraviolet and X-rays have a fairly high amount of energy. So we can see that EM waves with higher frequencies, that is, shorter wavelengths, will have more energy than those with lower frequencies. So radio waves have the lowest energy of any electromagnetic radiation, and gamma rays have the highest energy of any electromagnetic radiation. A certain beam of red light has a wavelength of 650 nanometers. What is its wavelength in meters? I hope you can remember your conversions. 1 nanometer is equal to 1 billionth of a meter. In scientific notation, that's writing 1 nanometer equals 10 to the power of minus 9 meters. So, how can we convert this 10 to the minus 9 into an answer here? As you can see, there aren't any minus 9s. The trick is that we have not 6 nanometers, but 650. So we're multiplying 6.5 times 10 to the 2 by this number. Can you see what's going to happen? If we have 1 nanometer as 10 to the minus 9 meters, 650 nanometers will be 6.5 times 10 to the 2, that is 650, times 10 to the minus 9 meters, which gives us, of course, 6.5 times 10 to the minus 7 meters.